Oh, hello. In this video of our machine learning using R series, I want to talk about dimensionality reduction by SOM. So SOM here stands for self-organizing maps. First, a brief overview. Self-organizing maps are unsupervised neural networks that project high-dimensional data onto a low-dimensional, usually 2D grid while preserving neighborhood structure. So each grid node stores a prototype called code book vector and similar data points mapped to nearby nodes on the grid. Learning uses competitive updates, the best matching unit BMU and its neighbor move their weights toward each input with the learning rate and the neighborhood size decrease over time. SOMs are widely used for clustering, visualization, anomaly detection, and exploratory analysis of unlabeled high-dimensional data. They combine nonlinear dimensionality reduction, clustering, and visualization in a single framework without needing labeled data and backpropagation. So this is a very powerful method and also very detailed. To implement SOM in R, we can use the package called Kohonen, K-O-H-O-N-E-N. Okay, and you can simply install it by using install.packages Kohonen here. And since I already did that, I'll just load it in. Create a sample size 500 dataset with 8 features, and then create 3 clusters, and then put them together in the simulated data set. Give them column names, and also we add some nonlinear relationships. So for SOM is actually has a nonlinear dimensionality reduction, so it's more powerful than PCA for linear dimensionality reduction. Okay, so here we actually say the first column to be squared of the second column plus normal error, and the third column is a sine function of the fourth column plus a normal error. Okay, so we can print out the summary statistic of data matrix. And then before we can do SOM, we have to scale the data set just using the function scale. And then we need to specify a SOM grid. So in this case, we specify 5 by 5 hexagonal grid. So use the sum grid function, x dimension equal to 5, y dimension equal to 5, topo equal to hexagonal. So we have 25 nodes. Okay, and then we have to train SOM using comprehensive parameters. So we can use the R length equal to batch for batch training and user weights for feature importance. Okay, so the main statement is this function SOM sim data scaled. This has to be a matrix. You cannot use a data frame here. Okay, and grid equal to sum grid. So these two are the basic arguments. The other parameters like the R length equal to 1000, alpha, radius, mode, user weights, and what's map equal to 1. Please refer to the help documentation for the meaning of these arguments. Okay, so I'll just run this. It's converged very quickly in this small data set. And now we need to do a comprehensive visualization using this package for the SOM we fit it. So first, let's split the screen to 2 by 3. First, we just plot out the change. That's the learning curve showing convergence. So for this case, the error rate, the error drops a lot at the initial iterations and pretty much stabilized after 240 maybe. Yeah. So then converged over time. So this shows good convergence. A second is property trajectory, called code book evolution, to visualize any numerical property mapped across your SOM grid. Red color means far away from original data. Blue means small adjustment. Smooth color gradient means topology preservation. Okay, so this is look like it's large adjustment from original value and pretty smooth. So means good topology reservation. The second plot is the count of sample per unit. Look like that, and the color intensity is proportional to the sign observations. So you have the red color, the blue, darker color means more observations assigned to that node. So here you can see majority of them has a lot, and then you also have about 2 nodes that has smaller numbers. Okay. The third one is you want the quality measures, this distance between neighbors units. So here, look like that. So the color, cool color like blue denotes similar prototypes, and warm colors marks the boundaries. So here you can see there's a one, meaning on the right corner with very white, very light color, cool color. But for the others, they're mostly like a boundary between the units. So overall, it's a pretty good separation from the data set. The second one, the next one is a little bit more complicated. It's the mapping of data onto SOM samples mapped to SO grid, colored by a rainbow scheme. It look like that. So you can see projects all the 500 data points onto the 25 node SOM grid and colored by their sign value by using a rainbow palette. Okay, and this is too small, but you can see the different dots is for individual data points, and if you see a dense region, meaning there's many dots, many data points in there at different nodes. Okay, and then the last one is the code book vectors and prototype vectors. It's the Venn diagram of scaled prototype vectors for all 8 features per node. And the longer spokes indicate higher feature values, and similar fan patterns indicate topology preservation. Okay. So, okay. So this one is the last one is the component planes, one for each feature, shows how each of the 8 features vary continuously across 25 node Hexagonal SOM grid. Okay, so here, let me do this. So this, we have 8 features. Remember when we create the simulated data set? So this is look like 8 features varies continuously across the 25 hexagonal SOM grid. So here, for example, you can look at feature 1. It has higher feature values and it form a connected zone. Okay, and feature 2 and 5, you look at 2 and 5, they have very similar patterns. They meaning they have positive correlations. And if for some with very different, like 2 or 3 has different patterns, that means they have negative correlation. So you can read a lot about the relationship between these features, from these component plane plots. Okay. All right. The last one is you want to plot the distance matrix between SOM units. Look like that. So this is uh, the blue color meaning cluster interior, yellow color means cluster boundary, and gray means empty or low count nodes. So here you can see these three colors, blue and yellow or green and gray, they are pretty well separated. Okay. So this indicate the SOM training for this artificial data set is pretty good. Okay. All right, let's do hierarchical clustering based on the SOM units clustering. You can create this hierarchical clustering plot showing you, different clusters. And then you can also extract numerical values for the classification and the errors, and you can print them out. Okay, so you can see it gave you the grid dimensionality and training iterations, quantization error, so 0, so very good dimensionality reduction. Number of empty units, 0, and then you get distribution. You can see from 1 to 25, these are nodes, and then the counts are the data points inside each node. The last step is really this. You can prepare your data set for the super SOM separation, preparation for multiple data sets. So I'm not going to demonstrate the super SOM here. I'll try to do it in another video, but here you can actually save your SOM model on the similar data and the similar scaled data into a data set, and then in the future, you can use the super SOM to analyze multiple data sets. Okay, I hope this serves as a good introduction to SOM analysis in R. Thank you for your continued support. Please subscribe to our learning channel, like our video, and click on the notification button. Thank you.